My name is Karim Akhnouch. I'm a senior solutions architect at AWS. I've been with the company since almost 3 years, and I've worked with many of the big manufacturers in Germany, helped them navigating the complexity of deploying GenAI applications.
Okay, perfect. My name is Mohammed Salah, working as a solution architect at AWS, looking after public sector in the Middle East. My job at AWS is solving the similar problem, not Karim's daughter problem, but the real manufacturer problems. Picture this, the same silence inside your factory, and you have machines stopped, your production line pause, everyone starts running around. Every minute, your products are not made. Your orders get delayed and costs pile up. Simply, this is what we are calling this silence unplanned downtime. The top 500 manufacturers globally, they are paying for this $1.4 trillion due to this unplanned downtime. They are losing around 11% of their revenues every year. To make this more clear, we are talking about this is equivalent to the GDP of the nation like Spain. When we take a closer look about this, we found 4 different challenges. First is the data silos. You have a production line, and as part of this production line, you have multiple machines. Each machine has its own alarms and telemetry data, but each machine has its own separate database. It will end up, you don't have this kind of a view, end-to-end view, to understand exactly the relations between the machine inside the same production line. The idea here is you have the data, but the data is disconnected. Second problem, which is the skill gap. It's all about people. For each manufacturer, you have this senior expert who can tell you from the sound of the mixer, there is a problem. This is over-mixed dough. Can tell you from the oven, the right side of the oven is much more heater than the left side. This kind of expertise, if they are not there, and you have a junior receive this kind of a warning, they will not be able to act. And this is the second idea. You have the knowledge, but knowledge is not shared. Third is the production delays, and this is when this silence feasible for everyone. You have the junior, you don't have those seniors. You have the data, but the data is scattered, and they are not able to act because they don't have the expertise, they don't have the knowledge, and the data is disconnected. Last one is the operational disruption. I know this is very important for every factory because most of the factories are in remote areas. When we are talking about the factory, they are not having, most of the time, stable internet connectivity. And they don't have a cloud access. If you have a smart manufacturer and this disconnected under any reason, this means your manufacturer will be blind. You will not have this kind of data-driven decisions and insights. That's why we thought about simple solution. Let's put all the data together in a one single data lake inside AWS Outpost. But when we did this, we found a different challenge. Each machine has its own integration type. I bought this machine from OEM X, OEM Y, and OEM Z. However, each OEM has its own integration, even technology. If we are talking about modern IoT integration, MQTT, or even LoRaWAN, or we are talking about REST APIs for post-HTTP and GET-HTTP. And most important part about your manufacturer is the documents. Those kind of standard operation procedure document, manual documents, you can get it using a legacy SFTP. We thought about why not to have this outpost underlying infrastructure over EKS local cluster, doing this unified API deployment to absorb those kind of different integrations. And accordingly integrate this with a one consolidated data lake, and then to get the consumer of this data lakes will be an AI, in our case will be Bedrock, and also to get much more insight with the dashboard using Amazon QuickSight. This will be the result. You have, on the left side, you have a production line. You understand everything. You have the full details and full understanding about your production line. As you can see, the inspector is telling you, you have a cracked cookies. The machine state is down for 5 minutes. Second problem is the resiliency, what we are calling always on. How to stay always on. If you got disconnected, outpost disconnected from the cloud, under any reason, you will not be able to act as a smart manufacturer anymore. You will not be able to have this kind of data-driven decisions. You will not get automated AI recommendations. That's why we thought, why not to add this intelligence at the edge by deploying multiple small language model. We'll go through this later as part of the sessions, and to have two different features. First, to provide intelligence for the operators using text and even voice to chat with the data. Second is to apply this kind of an automation. You are digesting your data and telemetry data every 5 minutes, understanding the insights, getting recommendations, and if you feel if this is recommendations require a notification, notify the operator with the required actions.
So before we jump into the coding session, which I know you're so much looking forward by now, please allow me 2 more minutes to explain the big picture so you understand how the end-to-end workflow looks like. We imagine having a cookie factory, which produces the best-in-class cookies here in Vegas. And for simplicity, this cookie factory has 3 big machines, which are the cookie former, followed by the freezer tunnel, and lastly, the cookie inspector. Now imagine the situation when the cookie inspector, which does the visual quality inspection, detects a cookie which is cracked, misshapen, or a cookie with some air pockets. Then we have our Agentic AI application running inside AWS Outpost for the always-on connectivity thing. This Agentic AI application has access to different data sources, including the machine manuals, the standard operating procedures, and real-time telemetry data and alarms. And then operators inside the production site can chat or voice chat with the agent to understand what is the underlying problem. And then it can finally instruct the agent to itself take some actions to correct the problem inside the production site. And finally, we move from the state where we had a cracked cookie to a state where we are producing delicious cookies and everyone is happy again. But you know what the problem is with what I'm showing here? I wish that the solution was as simple as plugging in the icon of AWS Outpost. Under the hood, there is a little bit of a more complex architecture. So on the right-hand side, we have the pipeline for data preparation and model fine-tuning, which we'll go into very details at the rest of the session. And on the left-hand side, we have our Agentic AI application deployed on AWS Outpost. And then we have different specialized small language models. We have GPT OSS model, which will be the routing model to navigate the different tasks from the users to the different tools. We have the fine-tuned Llama 3.2 billion parameter model, which will be specialized into the RAG application. And we finally have the small VLM for visual quality inspection. For sake of time, we will not be implementing the small VLM, but we will go through every other details of the implementations. So let's code. Okay, so I hope you're seeing my screen. You do? Right? So I will start with setting up the infrastructure deployment. And I will be mimicking this with a couple of EC2 machines. I will be mimicking the AWS Outpost environment with a couple of EC2 machines. So let me navigate to the first method here that we have, which is the create EC2 instance. And here, as you can see, I'm using the G4DN.X large instance, which is relatively small but capable instance. It can be capable of running a small language model. I'm selecting a specific AMI, which is the NVIDIA one, and then I'm creating some security groups, some VPC, some IAM role, and so on and so forth. But the most important part that I would like to stress on here and grab your attention is this part, the user data script, which will be uploaded to the EC2 instances, because this is the one that will be installing the actual dependencies that is needed to run the Agentic AI application. So if we take a look at, for example, this EC2 machine, the user data script of this EC2 machine, you will find that it's 148 lines, so it's not very realistic to go through this line by line. But instead, what I would like to do is I would like to use here your brains to brainstorm together what should be the dependencies that should be added to this EC2 machine. So please take a moment, scan the QR code, and think as if you are deploying this application, what dependencies do you need on the EC2 machine in order to host an AI agent and a small language model, which is the router small language model. Please think about it, and in a moment, I will be showing some results.
Karim.
Okay, so we're still collecting the votes. So you guys almost nailed it, right? Yeah. So of course we need the agent code. That goes without saying. We need Docker runtime because we will use Docker to pull the container of Olama, which will be our software for hosting the small language model. We don't need the fine-tuned model for this specific EC2 machine because we are having another EC2 machine where we will be deploying the fine-tuned model. We need the NVIDIA toolkit for the CUDA software. We need a custom Python version, indeed, because the SDK that we will be using for installing the AI agent is Strands. And Strands works with a minimum Python version of 3.10. And the default Python version in the G4DN instance is Python 3.9, which is why we need to install a custom Python version. And the one who said Olama, that's actually correct because we will be running Olama as a Docker container. Okay, so that was for the first EC2 machine for running the agent. Now please, again, scan the QR code and think what the dependencies do we need for the EC2 machine that will hold the fine-tuned EC2 instance, the fine-tuned small language model. Okay, so let me view the results.
Okay.
Yes, yes, yes. We need Docker, we need the fine-tuned model. In that case, we don't need a custom Python version anymore because it works with the default version of the G4DN.X large. That was a tricky question. We don't need the agent code that was deployed on the first EC2 machine. And we need Olama, and we need the SLM, of course. Okay, so I'm happy that we will brainstorm the dependencies. Now, after we write the user data script, like I said, we create a VPC, we create security groups, we create an IAM role with access to S3. And when we are happy with that, we need to deploy our application.
Perfect. Now, we have infrastructure starting to deploy. Karim will debug for sure what is going on. But during this time, let me give you some tips and tricks how to do a deployment for a small language model over AWS Outpost. We'll take a closer look here. The GPU instance that we have over Outpost is the G4DN. And to deploy any model, you have to consider two things. First is the hardware constraint. We are talking about G4DN 12x large, which is 4 T4 NVIDIA instance, each one of them powered by 16 gigabytes of memory. At the same time, and this is the second consideration, is the model itself. We are taking an example of an OpenAI model, OSS, around 20 billion parameters. But here I mentioned different parameters, which is very important to consider while doing a deployment over the Outpost. One of them is, if this is a mixture of expert or not, how many layers, and the active parameters per token. Now, let's focus on the first strategy to do the deployment, is the quantization. Quantization, in a nutshell, is reducing the number of bits presenting your weights in order to reduce the memory footprint. This model trained by using the precision of FP16. This is the base model. However, we can have another quantization, which is MX FP4. We are talking about how to present each weight. We are talking about how to present each parameter. Instead of presenting each weight with 16 bits, you can present the same weight with 4 bits. This will make a significant reduction in the memory footprint. Instead of having the full precision, which is the base model, 40 gigabytes, you can get only 13 gigabytes. But everything came with a cost. The cost here is accuracy. For the base line, you don't have an accuracy impact. However, for mixture of FP4, because you are going to reduce the number of bits presenting your weights, you will have 1 to 2% accuracy impact. This means that you can save 65% of your memory, trading this by 1 to 2% of accuracy loss. By doing this, you will have the full model can be deployed with the 13 gigabyte in your memory. Do you remember the hardware constraint? We have 16 gigabytes. Now you can have the full model deployed inside GPU. One of the deployment strategy is to deploy the full model in a one GPU. As you can see here, we are going to replicate the same model across the GPUs. And the significance of doing this is to have latency-sensitive workload implementing by doing a parallel processing for multiple clients at the same time. Your application will not have any kind of a tolerance for the latency. You are going to do a processing in a separate GPU for each client. Second strategy is this. You have one single model, weights, sharded across GPUs, where for each GPU you will have 3.2 gigabytes for the model weights. And the remaining will be for the KV cache. KV cache is simply, this is how to cache the tokens as part of your session in order not to let the model recalculate the token every time generating a new content. If you have a larger KV cache, this means that you can get large number of users, and at the same time you can get a larger context window. And this is important for your session. Let me show you the foundational part of this. We started with the architecture, high-level architecture, where we can start with the data preparation. Let me show you something with the data here. As you can see, those are the data sources. You have a different types of data sources. You have a CSV files, you have a text files, and you have a PDF files. This is the normal data source, how it look like. You have a different files, you have a different formats, because you have in your production line, you have a different OEMs, and each one of them has its own structure to do this. What we need to do is to fine-tune the model. But what is the objective of the fine-tuning the model? The objective here is to give an assistant for your operators. This assistant will help your operator to have a detailed, instructed steps with considering the severity of each problem, considering the compliance, considering the safety, and so on and so forth. The most important part is to let the model understand the skills needed and let the model talk with the same tone needed. That's why we decided to use a fine-tuning the model using instructed fine-tuning. Let's start with what exactly happening under the hood. I will show you here in the right side, as you can see, this is a data pipeline where you can read the different documents, PDF file, text file, and document files. And then you can invoke a larger model in order to generate a structured data to fine-tune your model. The most important question here, why to not through the data to the model directly to fine-tune the model? The answer is simply is, if you are throwing your data right away to your model, you are training a hallucination machine. The important part here, reading the document, invoking the model to return a structured data, accordingly validate those data, and then you are happy to have a full structured documents in order to fine-tune the model. Let's start with running this. As you can see, the pipeline starts reading this and at the same time start invoking the Bedrock to generate questions and answers. Why to generate the questions and answers? In order to have an instructed data set in order to fine-tune your model. Let me show you something here. This is the data preparation class that we are using to invoke the model. As you can see, here we are using this model to generate the structured data. And the most important part of this is let me show you something very important, is the Converse API. As you can see here, we are using the Converse API. Converse API is giving you the flexibility of changing any model at any point of time because it's using for different models, same API signature. At the same time, and the most important part is the inference configurations. If you are configuring the maximum number of tokens correctly, you will be able to get your answer correctly without having any kind of data splitted or something. The most important part here is the system prompt. This is an instructed prompt with the only one shot. I'm giving the model a clear and detailed instruction to generate the realistic information, to include the severity, to answer the safety questions correctly, and include the needed information. By doing this, you will be able to have a full data set with your structure, with structured data. Second, and this is very important, why do we need to trust the LLM? Maybe the LLM itself will hallucinate. In this case, if your LLM is hallucinating, you have to apply what we are calling a deterministic validations. Yes, the LLM generated the content, but if the content is correct, if this is a right question and answer, if this is following what a standard operation procedure is telling you if this is following even the needed structure for for your response in a JSON way. Why this is important? Because again, we need to make sure that we are not having a single record in your structured data for the fine-tuning the model. Second is sharding. If you are starting to shard your data, you have to shard your data in a smart way. If you have a very long paragraph, you cannot cut the paragraph in between. If you have a large section, you have to make sure that this section is splitted in a correct way. You cannot split a sentence in the middle. Why this is important? Again, same objective, structured data implemented correctly. As we can see on the right side, the job is done, and we have generated Q&A done, validation done, and as you can see, we have some statistics here. We have a 50 pair of questions and the answers requested, 45 generated, and we have 5 rejected. We can check here the output file, and from the output file, you can see this is rejected because of the frozen belt misalignment section. This is the content, and this is the critical information, which is wrong. Why? Because the model itself, or the pipeline itself, is doing this validations across the needed structure and across even the data inside the SOP. Accordingly, now we uploaded the data inside S3 in order to start the fine-tuning the model. I'm not sure if you are familiar with this. This is AWS SageMaker AI Studio, where you can start to fine-tune the model. If you go on the left, you can see this is the jump start. Inside the jump start, you can select the model. Here, the model family is Meta. This is a model family. Perfect. Llama 3.2 billion instruct. This is our model. Here you will find the 3 different options, either to evaluate, deploy, and train. In our case, we are going to train the model. So I'm going to select training the model. After selecting the model, you have to select the data set. We did as part of the data preparation for the data set. Here is the data set. Here is the data we just uploaded. We select the data. And then we need this fine-tuning. There is an output of this fine-tuning or updated weights of your model based on your data set. You are going to set the S3 bucket to get your updated model. Accordingly, you can go through this. I think it is normal to have 5 epochs. And this is very important. This is AWS recommended recipe to do the fine-tuning using this G5 instance. If you want to select a different instance, it is fine. This is fully flexible, but this is what we are recommending as part of fine-tuning the model. Accordingly, we are going to use the same identity access management, same VPC, same encryption keys, and then we'll submit the model. We have to agree on those things. And then job started to do the fine-tuning for the model.
Okay, so now I bet that many of you is asking themselves one question, which is, in my opinion, very valid if you are asking it. And the question is, why are you guys doing this model fine-tuning and data preparation when you will anyways be using a RAG task in the edge? Maybe you are asking yourself if we just added this piece of architecture in order to make our architecture looks a little bit more fancy. Well, while we may love doing so, but in fact we have done extensive experimentations in order to prove that this approach is indeed valid. And in order to prove that, we have used a technique which is called LLM as a judge evaluation. And let me show you how this technique works.
صورة شوي.
أنا مش عارف. Okay. Please allow me a moment.
خلاص تمام.
Yeah, for some reason, the aspect ratio is not working well.
في البراوزر خلاص مش مشكلة.
Okay, so let me explain how LLM as a judge evaluation works. I had some fancy animation, but anyways. So we have our fine-tuned model, and we have our base model, the Llama base model that is produced by Meta. And we want to compare the performance of both models on the RAG task. So how it works, at the very first step, what we provide to both models is the question and the context from the test dataset. And we ask both models to generate an answer based on those question and context, because usually this is how you do it in RAG applications. And then as a next step, we have our 3 LLM as judge evaluators. We have Claude 4.5 Sonnet, we have Claude 4.5 Haiku, and we have Amazon Nova Pro as judges. And we pass to each of those 3 judges 5 different inputs. We pass the question and the context from the test dataset that Salah has generated. We pass the answer from the fine-tuned model from the previous step that I just showed. And we pass the answer from the base model based on the question and context. And finally, we also pass the ground truth answer from the test dataset. And we ask each of those 3 models to evaluate the result generated from the fine-tuned model and the base model based on 3 evaluation criteria, which are number 1, accuracy, which measures how well the result from the fine-tuned model and the base model agrees with the ground truth answer from the test dataset. Number 2, evaluation criteria is the completeness, which measures how well the answer is addressing all the different aspects of the question. And number 3, evaluation criteria is the relevance, which is, in my opinion, the most important metric in the RAG application, because this one measures how well the answer is following the context given to it, because this is how RAG works. And then we ask the 3 judges to evaluate the performance of the base model and the fine-tuned model. And here we have the results of our LLM as a judge evaluation. In my opinion, this is really great results, because this shows that the different evaluators, different evaluator models, shows that the fine-tuned model is outperforming the base model in the RAG task for all the test dataset aggregated for all the 3 different evaluator criteria. So for example, Claude 4.5 Haiku says that the fine-tuned model is outperforming the base model by 17%. And Claude 4.5 Sonnet says that the fine-tuned model is outperforming by 15%. And Nova Pro says it outperforms the base model by 10%. So on average, we have 14 percentage points improvements for adding the fine-tuned model on the RAG application for our Agentic AI application. So now let me quickly recap before jumping to the next step. We started with deploying the infrastructure to our EC2 machines in order to replicate or mimic the environment of AWS Outpost to have our Agentic AI application. Then Salah thankfully showed us how to prepare the data and fine-tuned a small language model for the RAG task. And I just showed you how important this is in our architecture. Now we need to put this together into an agentic AI application that runs on the edge on AWS Outpost. And this agentic AI application will have access to the RAG tool and also the telemetry data tool. So let's start doing that. Okay, as you can see that our two EC2 machines are up and running now, the factory agent instance and the fine-tuned small language model instance. So what I would like to do is to log in to the factory agent instance. So I would use Kiro for that. I installed a plugin for remote SSH. I connect to the host. And now it's opening an SSH session inside the EC2 machine, which we instantiated at the beginning. So now we are in the EC2 machine. I need to go inside the factory agent directory, which I copied in my user data script. I zoom in a little bit. Zoom in is not working. Oh.
During this time, let me explain something very important. We used two different approaches here. We used fine-tuned model, and at the same time, we used RAG. Anyone have an impression why we did both? Because most of the time, you are using one of them. Any answers? Huh?
Information that you're storing in the right database may be updated in the future, and you don't have to retrain a fine-tuned model in order to support that.
Exactly.
Yeah.
And let me dive deep into this. The most important part here is to have the knowledge about your document and the skills needed. To fine-tune the model is you are gaining the skill needed. You are setting the tone of your agent to respond correctly. By having a RAG, you are retrieving up-to-date information from your knowledge base. That's why we combine both to achieve this LLM as a judge evaluation results. We are talking about 15% increase from the base model.
Cool. So now, as Salah is talking about the RAG tool, I would like to start with showing you how to develop that RAG tool that I will be using for my agent application. And I pre-created this class, which is called RAG Retriever. Previously, I also, in my environment, I pre-ingested the documents inside ChromaDB as a vector store. And I created a very simple method, which is a search method that you can provide it with a query and the number of results. And then it uses this query to look up the information inside the vector store and retrieves the most relevant information from within your vector store. And then I use the tool decorator from Strands SDK in order to have this search documents method. And here I'm providing some docstring, which will be used by the agent to understand what this tool is doing and how it can actually be used. And then, as you can see, we are iterating over the results of the retrieval from the vector store, and we are printing them in a nice format. So this is a tool for RAG, retrieval, augmented, and generation. Do you think in this implementation here, anything is missing here? Again, we have retrieval, augmented, and generation. Anything you see missing in this tool implementation?
A major thing.
Okay, just to save your time, we have the G missing, the generation missing. If you remember the model that Salah spent some time fine-tuning, we're not using that model here, right? And what I would like to show you is how to use that model in order to enhance the results like I showed in the LLM as a judge evaluation. So what I will do, we will be instantiating OLAMA client using the IP address of the machine which has the fine-tuned model with the port that opens up the OLAMA connection. And then I need to just copy and paste couple of code parts. I will just paste it here. Yeah, and then I change this to response. Okay, so now we have our RAG tool complete, at least in my eyes. We have the retrieval part, and we have the generation part, asking OLAMA to invoke the endpoint of our fine-tuned model, passing to it the query and the result. So this was the first tool, and this tool was to retrieve the standard operating procedures and the manuals from the different machines inside your production line. Now the second tool is the telemetry tool. And this telemetry tool is to retrieve real-time telemetry data and alarms from your machines inside your production line. And I have mocked this real-time data by a very simple CSV file. As you can see, I'm not sure if you're seeing. Let me zoom in a little bit. As you can see, the CSV file has a device name, the sensor type of that specific device, the reading, and the timestamp for that reading. And we have two devices. If you remember from my first slide, we have freezer tunnel machine and the cookie former machine. And for each of those two devices, we have two different sensors, the temperature and the speed. And then we have the reading for those different sensors. And finally, the timestamp at that specific reading. So for the telemetry tool, I also pre-created a class, which is the telemetry reader that reads this CSV file. And then I also created another helper method which converts this CSV into a time frame. And we pass to this method three things. The device name that we want to look for, that we want to look the telemetry for, the current time where we are standing, and the number of minutes back in time where we want to look at. So for example, if we want to look the telemetry data for the last 5 minutes, we set the minutes back here to 5. And here, if we, for example, provided as an input the device name corresponds to freezer tunnel, this is how the output can look like. So the freezer tunnel has temperature and speed sensors, and those are the readings for the different timestamps. Now I want to create a strands tool out of that one. So let me create it as we go. If you remember, I would use the tool decorator. I would create a method called get telemetry data. And for that method, I need a device name, which is of type string. And I need minutes back, which is of type integer. And the return should be here a formatted string. Again, for any tool, we need to have a well-structured doc string. So I will be copying the doc string from my notes here. And then we need to code the tool. So this method here instantiates the class telemetry reader. We need to have it. Get telemetry reader. And in order to call the method which I showed you before, which is this one here, we need the device name, which is passed as an input. We need the minutes back, which is also passed as an input. And we need the current time string. Luckily enough, Strands has its own implementation of current time, so we will be using that one. Current time string equal current time class from Strands. And finally, now we need to call the method that I just showed you. Data frame equal till reader dot get device sensors and time frame. And we passed with the device name that we have as an input. We passed with the current time string. And we passed with the minutes back. And now we just need to formulate our results in a nice F string. Readings for device name for the last minutes back minutes. And then we just need to concatenate the results that we get from the method. Result plus equal JSON.dumps. And then we have the data frame, and we set the indentation to 2. And finally, we return the results. Cool. So as any good software engineer, I wrote a tool. I just need to test it. Let me do that very quickly in order for the application to work at the end. Get telemetry data. And we need to have one device from our CSV file, which is, for example, the freezer tunnel for the last 5 minutes. Okay, yeah, I always do this problem. It should be only return result. And now it works. Okay. So now you can see that we have our readings for the freezer tunnel for the last 5 minutes structured in a nice JSON format. So the final thing that I would like to add here is a very simple tool inside this telemetry tool, which is a tool that can be used as a lookup for the agent to understand which devices that it has access to. Think about the situation here. For example, I type freezer_tunnel, which is the name that I just copied and pasted as is from the CSV file. In real life scenario, users don't know how the exact name is written inside your database. So we need to have some sort of a lookup so that if, for example, the user typed had a typo or typed it without the underscore or had a capital small letter or so on and so forth, this shall work. So let me just copy and paste the last tool, list available devices. And that should be it. And now the last fun part, which is the agent, which puts all those things together. And so I pre-created this class, which is called Factory Agent. It uses the GPT OSS model, the edge model that I deployed at the beginning of the session. And here, it uses this big system prompt. I would like to walk you through the prompt and how I structured it because it might be relevant to you. So the first thing that I pass to the prompt is some orientation to how the tools look like. What tools does it have access to? And the second thing is some scenarios, some possible scenarios and examples of users' interaction. And based on those user interactions, what tools that the agent should be using one after the other. So it's some sort of a few-shot prompting here. Right. And then we have the system prompt, we have the model, and we have the tools I imported from the class. We instantiate the strands agent, and we are good to go. Finally, we need to test our agent and see how the result looks like. Before the session, I asked my best friend Kiro to create a nice UI that I will be using to test my agent. So I will be just invoking this agent, this UI. And here we have our UI. So now, since we have our agent, I would like you to put yourself into the shoes of the operator inside the cookie factory. Remember my first slide, when the visual inspector has detected a problem inside the cookie. Now you are a junior operator inside this cookie factory, and you want to understand what is the problem. You know that the visual quality inspection has two devices in front of it, which is the freezer tunnel and the cookie former machine. So as a junior operator now, what I would do is ask a very simple question: debug freezer tunnel. That's a very simple, but it's a powerful enough prompt in order for the agent to understand or try to resonate what is wrong with this freezer tunnel. And as you can see, it used the listing devices because I didn't use the 100% correct name of the device inside my CSV file. It used the get telemetry data tool that I just coded, and it used the search documentations tool that we also have written for the RAG. Let's see why that. And as you can see in the results, I will make it bigger in a second. What it did is it retrieved the telemetry data and it compared the telemetry data with the correct results from the documentations to see if those measurements make sense or not. And in our case, it detected that the temperature is not in the correct range. And here it also suggested some follow-up actions in order to debug this machine, in order to restore it to the operating state.
Okay, perfect. This is what happens when you have a factory start listening. Everyone and everything inside your factory are now talking with the same language, which means machines, IoT sensors, systems are fully integrated together, where you can have an AI system that can gives you a different types of recommendations, explanations, insights about your factory. The important part here, and this is the key takeaway, is we connected the operations by having a full deployment over Outpost EKS local cluster. In case of any disconnection, you still have access to your control plane, you still have access to your data plane, and you can manage your infrastructure completely in case of any disruption. Second is deploying a small language model at the edge, which makes this kind of intelligence real-time intelligence. You're understanding what exactly you are deploying the agents, getting the insights, and then giving a recommendation on the fly. Third, and this is very important part, is you are still generating more data every day, and you have to stay continuously learning and continuously understanding, because the data is your gold. Once you got this data, update your model, trigger the pipeline again, and fine-tune the model. I encourage you to scan those 3 QR codes to do the full end-to-end deployment of an Agentic AI, a small language model at the edge. Okay, now it's your turn to start with one single process. Get some data. Start to understand your manufacturing production line in a more detailed way. Start small, fail fast, understand your data, structure the data in a correct and proper way, and then fine-tune the model. Get the fine-tune the model. Speak your language, generating the correct information, and then doing the deployment on the edge over the outpost. Thank you, and it was really a pleasure having you as part of this session, and I encourage you to take the survey and give us the CSAT. Thank you. Thank you.